direct current solenoid's inrush current multiplier is approximately 10 to 20 times the steady-state current. This means that when a direct current solenoid is initially energized, the current flowing through it can be significantly higher than the current it draws once it has reached its operational state. Understanding this inrush current is crucial for designing robust and reliable control circuits for the solenoid. Firstly, let's define what a direct current solenoid is. It's an electromechanical device that converts electrical energy into linear mechanical motion. It consists of a coil of wire, often wound around a hollow bobbin, and a movable plunger or armature. When a direct current is applied to the coil, it generates a magnetic field, which then pulls the plunger into the center of the coil. This motion can then be used to actuate various mechanisms such as valves, switches, or levers. The steady-state current, also known as a holding current, is the current that flows through the solenoid coil once the plunger has fully moved into its activated position and remains there. This current is sufficient to maintain the magnetic field required to hold the plunger in place. The inrush current, on the other hand, is the peak current that flows through the solenoid coil at the instant it is energized. This current is much higher than the steady-state current because, at the initial moment of energization, the plunger is not yet in its final position and the coil presents a lower impedance to the current flow. Several factors contribute to the high inrush current of a direct current solenoid. One of the primary factors is the inductance of the coil. Inductance is the property of an electrical circuit that opposes changes in current flow. When a voltage is suddenly applied to an inductive circuit, such as a solenoid coil, the inductor resists the immediate change in current, causing a large initial current surge. Another contributing factor is the back electromotive force, or back EMF. Back EMF is a voltage generated within the coil as the magnetic field builds up. This voltage opposes the applied voltage, limiting the current flow. However, at the instant of energization, the back EMF is not yet fully developed, allowing higher initial current to flow. The inrush current multiplier, which is typically in the range of 10 to 20, quantifies the ratio between the inrush current and the steady-state current. For example, if a direct current solenoid has a steady-state current of 1 amp, its inrush current could be as high as 10 to 20 amps. The exact value of the inrush current multiplier depends on various factors, including the design of the solenoid, the material used for the coil and plunger, the air gap between the plunger and the coil, and the applied voltage. Understanding the inrush current multiplier is essential for proper solenoid selection and circuit protection. If the control circuit is not designed to handle the high inrush current, it can lead to various problems such as component failures, voltage drops, and even damage to the solenoid itself. To mitigate the effects of inrush current, several techniques can be employed. Firstly, using a current limiting resistor in series with the solenoid coil can reduce the inrush current by adding additional resistance to the circuit. The resistor limits the initial current surge, preventing it from reaching excessively high levels. The value of the resistor should be chosen carefully to ensure that it provides sufficient current limiting without significantly affecting the solenoid's performance during steady-state operation. Secondly, employing a soft-start circuit can gradually increase the voltage applied to the solenoid coil rather than applying it abruptly. This allows the magnetic field to build up more slowly, reducing the inrush current. Soft-start circuits can be implemented using various electronic components such as resistors, capacitors, and transistors. Thirdly, utilizing a snubber circuit can help suppress voltage spikes and oscillations caused by the sudden change in current. A snubber circuit typically consists of a resistor and a capacitor connected in parallel across the solenoid coil. The capacitor absorbs the energy stored in the inductor, while the resistor dampens oscillations. Fourthly, selecting a solenoid with a lower inrush current can also be an effective solution. Solenoid manufacturers often provide specifications for the inrush current of their product. Choosing a solenoid with a lower inrush current can simplify circuit design and reduce the need for additional protection measures. When selecting components for the solenoid control circuit, it is important to choose components that are rated to handle the inrush current. This includes selecting appropriate fuses, circuit breakers, and transistors. Fuses and circuit breakers should be sized to protect the circuit from overcurrent conditions, while transistors should have a sufficiently high current rating to withstand the inrush current without being damaged. The effects of temperature on the inrush current should also be considered. The resistance of the solenoid coil increases with temperature, which can affect the inrush current. At higher temperatures, the resistance of the coil will be higher, which will tend to reduce the inrush current. Conversely, at lower temperatures, the resistance of the coil will be lower, which will tend to increase the inrush current. These temperature effects should be taken into account when designing the solenoid control circuit. In summary, the inrush current multiplier for a direct current solenoid is an important parameter to consider when designing control circuits. Understanding the factors that contribute to inrush current and implementing appropriate mitigation techniques can help ensure the reliable and safe operation of direct current solenoids. Proper solenoid selection, circuit protection, and component selection are all essential for managing inrush current effectively. For example, let's consider a direct current solenoid used in an industrial automation system. This solenoid is responsible for actuating a valve that controls the flow of liquid in a pipeline. The solenoid operates on 24 volts direct current and has a steady state current of 0.5 amps. Based on the inrush current multiplier of 10 to 20, the inrush current could be as high as 5 to 10 amps. To protect the solenoid and the control circuit from the high inrush current, a current limiting resistor is added in series with the solenoid coil. The resistor is chosen to limit the inrush current to a maximum of 2 amps. This ensures that the components in the control circuit are not subjected to excessive current stress. A fuse is also included in the circuit to provide overcurrent protection. The fuse is rated at 2.5 amps, which is slightly higher than the maximum inrush current but lower than the current that would damage the solenoid or the control circuit component. Additionally, a snubber circuit is connected across the solenoid coil to suppress voltage spikes and oscillations. The snubber circuit consists of a 100 ohms resistor and a 0.1 microfarad capacitor. These components are chosen to provide effective damping of the voltage spikes without significantly affecting the solenoid's performance. The transistor used to switch the solenoid is selected to have a sufficiently high current rating. The transistor is rated to handle a continuous current of 5 amps, which is well above the expected inrush current. This ensures that the transistor can withstand the inrush current without being damaged. By implementing these protection measures, the direct current solenoid in the industrial automation system can operate reliably and safely. The current limiting resistor, fuse, snubber circuit, and high current transistor all contribute to mitigating the effects of inrush current and protecting the solenoid and the control circuit from damage. In another example, consider a direct current solenoid used in an automotive application, such as controlling the fuel injection system. This solenoid operates on 12 volts direct current and has a steady state current of 1 amp. The inrush current could be as high as 10 to 20 amps. In this application, a soft start circuit might be used to gradually increase the voltage applied to the solenoid coil. The soft start circuit can be implemented using a pulse width modulation (PWM) controller. The PWM controller gradually increases the duty cycle of the voltage applied to the solenoid coil, allowing the magnetic field to build up more slowly. This reduces the inrush current and prevents excessive stress on the solenoid and the control circuit components. A flyback diode is also connected across the solenoid coil to protect the transistor from voltage spikes caused by the collapsing magnetic field when the solenoid is switched off. The flyback diode provides a path for the current to flow when the transistor is turned off, preventing the voltage from rising to dangerous levels. The components used in the automotive solenoid control circuit are selected to withstand the harsh environmental conditions found in automotive applications, such as high temperatures, vibration, and exposure to chemicals. The components are also designed to meet the stringent automotive safety standards. By using a soft start circuit, a flyback diode, and robust components, the direct current solenoid in the automotive fuel injection system can operate reliably and safely under demanding conditions. It is important to consult the manufacturer's specifications for the specific direct current solenoid being used to determine the appropriate inrush current multiplier and to select the appropriate protection measures. The Inrush current multiplier can vary depending on the design of the solenoid, the materials used, and the operating conditions. It is also important to consider the specific requirements of the application when designing the solenoid control circuit. The control circuit should be designed to meet the performance requirements of the application while also providing adequate protection for the solenoid and the control circuit components. Additionally, it is advisable to test the solenoid control circuit under actual operating conditions to verify that it is functioning correctly and that the protection measures are effective. This can help identify any potential problems and ensure that the solenoid will operate reliably in the field. Furthermore, regular maintenance and inspection of the solenoid and the control circuit are important to ensure continued reliable operation. The solenoid should be inspected for signs of wear or damage, and the control circuit component should be checked for proper operation. Any worn or damaged component should be replaced promptly. In conclusion, understanding the Inrush current multiplier for a direct current solenoid is crucial for designing reliable and safe control circuits. By considering the factors that contribute to inrush current, implementing appropriate mitigation techniques, and selecting robust components, engineers can ensure the optimal performance and longevity of direct current solenoids in a wide range of applications. This involves a combination of theoretical understanding, practical application of protection measures, and attention to the specific requirements of each application.